Hello guys, in the last lecture we started with the sequence networks. So we saw that for different sequence components we designed different circuits. So first we looked at the case of a star connected winding. There we made an important observation that neutral impedance does not appear in the positive and the negative sequence network but only appears in the zero sequence network. And in zero sequence network it appears as 3 times Zn. Then we looked at delta connected winding and we observed that zero sequence currents can exist in phase but not in line. So what we did is we connected the winding to the reference bus and kept the line open circuited to indicate that there are no zero sequence currents in the line. Then we looked at the case of alternator, and the first observation that we made is as long as the direction of rotation of the rotor is same, the induced EMF will be positive sequence, that is EA, EB, EC. Then we saw the positive sequence network and observed that since fault current is 0 power factor lagging, it will lie along the d-axis and it also rotates at the synchronous speed in the direction of rotation of the rotor. So the relative distance between the rotor or the field axis and the armature MMF does not change and it always lies along the d axis. So we kept x1 is equal to xd. Then for the negative sequence network, the armature MMF rotates at synchronous speed but in a direction opposite to the rotor direction. So there is a relative speed of 2ns between the rotor MMF and the armature MMF, and hence it encounters xd and xq in an alternate fashion. So we kept x2 is equal to xd plus xq by 2. Then we saw zero sequence network. There we saw that all the three MMFs were equal and aligned at 120 degree with respect to each other. So their resultant was 0 and hence they did not produce any armature reaction. So zero sequence reactance came out to be equal to leakage. And we saw the order was x1 was greater than x2 was greater than x0. This was the order of the sequence impedances of a alternator. In this lecture we will concentrate on deriving the sequence networks for the case of transformer and the transmission line. So let us first start with the transformer. In case of a transformer, what happens is the equivalent circuit is something like this. If I have referred the entire circuit to primary, it will be something like this. This will be core loss resistance, magnetizing reactance, then winding resistance and leakage reactance. Now the current flowing in the shunt branch is called as no load current. And for the case of power transformer, it is almost 1% of full load current. And since we are drawing the sequence network to analyze the fault case, so fault current will be 10 to 20 times higher than the full load current. So we can neglect I0. Okay, that means we will disconnect the shunt branch. And as I told you, we have to neglect each and every component that makes the system stable. So resistance will improve the system stability in case of a fault. So resistance will also be neglected. So what we will have is, we will have a series reactance which is equal to leakage reactance. Hence, the positive and the negative sequence networks will be identical. They will just consist of a leakage reactance. Now, why positive and negative are identical? Because here there is no rotating magnetic field. Hence, the positive and negative are not affected by the sequence of the current. So, ZT1 will be equal to XL and ZT2, that is the negative sequence impedance, is also equal to JXL. This will be IA2. But the case of zero sequence current, as I told you, as we derived, zero sequence current can only flow in the lines of the star connection with grounded neutral or zero sequence currents can flow in the delta winding phase but not in the line. We derived that the line current can only contain zero sequence component in case the connection is star with a grounded neutral. Otherwise, it can only exist in phase of the delta. That means presence of the zero sequence currents depend on the connection of the transformer. So we have to judge, or the circuit will change based on the different type of connections of the transformer. So the universal circuit that we use for zero sequence network is this. Here we have two series switches. Let me name it as S1, S2, and two shunt switches S3, S4. Now S1 and S2 series switches indicate that the zero sequence current will flow in the line. That can only happen with star with grounded neutral. S3 and S4 will connect the impedance to the reference bus, and that we did in case of a delta connection. How did I show the presence of zero sequence current in phase? I connected the impedance to the reference bus. So they indicate delta connection. Okay. So whenever any winding is delta connected, we will operate S3 and S4. If it is star connected, we will operate S1 and S2. Now let us see one by one how we will design the circuit for the different cases of or different connection of transformer. First, let us take the case of star-star connection. Suppose we have star with ungrounded neutral, star with ungrounded neutral. That means star neutral is not grounded on either side. That means zero sequence current cannot flow on the primary as well as on the secondary. Since it is star connection, we will have to operate series switch. For this one, we will operate S1. For this one, S2. But S1 and S2 will be kept open because ground neutral is ungrounded. So this will be the zero sequence circuit of a star-star connection with a ungrounded neutral. Now as this circuit is open circuited, zero sequence current is 0. Which shall be the case because there is no neutral grounding, hence zero sequence current cannot flow. Now suppose if I ground this neutral, then this point here will be shorted. Okay, but still since this circuit is incomplete, IA0 will still be 0. IA0 can only flow if this circuit gets closed on both the sides. That is, if I ground on both the sides, then zero sequence currents can exist and this will be shorted. Then IA0 will not be 0. Okay. So, one thing that you must always remember, either the zero sequence current will exist on both sides of the transformer or it will not exist on any side, because in transformer currents are related by the turns ratio. Either the current will be present on both sides or it will not be present on any side of the transformer. Hence, we must ground both the sides of the transformer in order for the zero sequence current to flow. You cannot just ground one side and expect the zero sequence current to exist, because that will violate the transformer principle. Now let us generalize this case by placing the neutral impedance. Let me place a neutral impedance here. Z capital N, Z small n. Why I am using uppercase and lowercase? Because primary is represented in uppercase, secondary in lowercase. Now we studied in zero sequence circuit, the neutral impedance appears as 3 times the neutral impedance. So how the circuit will look like? 3Zn, then transformer zero sequence impedance, which is equal to actually JXL, then 3Z small n, and it will be like this. This current will be IA0. Now you can take the two extreme cases. Zn is equal to 0, which means solid grounding, and Zn is equal to infinity, which is the case of isolated neutral. So all the cases can be derived from this two special cases of the neutral grounding. Hence, we have taken a general case in which the neutral is grounded by means of a impedance. Okay. So you can either equate Zn to be 0, infinity, and Z small n and Z small n to be 0 and infinity. That way you can realize all the cases that we have done so far. So this is about the star-star connection. And remember, for star-star connection, we will not operate any of the shunt switch. Next comes the star-delta connection. Primary is star, we will operate S1. Secondary is delta, we will operate S4. Okay. That is a shunt switch. This is my series switch. Now first take the case when Z star is ungrounded and this is delta. Since the star is ungrounded, we will keep series switch open. Since delta is there, we will short the shunt switch. But now since the connection is open, IA0 will be 0. There will be no zero sequence current flowing in the lines of the transformer. Now suppose I ground this, then what will happen? This will be the case. So zero sequence current will flow like this. That is, zero sequence current can exist in the lines of the star connection and in the phase of delta. This you have to disconnect here because series switch is not operated. Okay. So here the zero sequence current cannot exist on the lines of the delta side, but it can flow in the line as well as phase on the star side. How? Because if any current exists in the phase of star, it will exist in the line of star, because in star connection line current is same as the phase current. So here zero sequence current will flow in phase as well as line of star, but only in the phase of delta. So let us again generalize this by placing a neutral impedance, that is Z capital N. So what changes we will do in the circuit? We will show it like this, 3Zn. Okay. So this is the equivalent circuit or the general circuit for the case of star delta connection. Next, let us consider the delta star. Now primary is delta connected, we will operate S3 here. Secondary is star connected, we will operate S2 there. Okay, this is my shunt switch. This is your series switch. Again, first let us consider the case of delta star ungrounded. Since primary is delta, we will operate shunt switch. Secondary is star, we will operate series switch. But since it is ungrounded, we will keep it open. So here zero sequence current on both the sides of the transformer will be 0. Okay. Now suppose if we ground this neutral, then this switch will be shorted. Then zero sequence current can flow like this. That is, zero sequence current can exist in phase as well as line of the star connection and the phase of delta. Here zero sequence current will be 0. To generalize this, we will place a neutral impedance on the secondary. This will be shown in the circuit in terms of 3 times the neutral impedance, like this. Okay. So that is the equivalent circuit for the delta star connection. Last, let us consider the delta delta connection. Here primary is delta, operate S2, sorry S3, secondary is delta, operate S4. Both are my shunt switch. So how we will draw the equivalent circuit? We will operate the shunt switch on primary, shunt switch on secondary. Okay, that means zero sequence current can flow in the loop, which indicates zero sequence current can flow in the phase of both primary and secondary, but it cannot go in the lines of either primary or secondary. So these zero sequence circuits are pretty important for the course, because sometimes a zero sequence circuit will be given to you and you will have to identify the transformer connection. In other cases, you may be asked zero sequence circuit given the transformer connection. So zero sequence circuit of the transformer is the most important topic in the sequence networks. Next, let us consider the case of transmission line. In case of transmission line, we will define two type of impedances, ZAA, ZBB and ZCC. This is one category, that is impedance of A due to A, impedance of B due to B, impedance of C due to C. Similarly, ZAB, that is impedance of A due to B, ZBC, impedance of B due to C, impedance of C due to A, ZCA. Okay, so these three will be mutual and these three will be self. Now we studied in case of transmission lines that in case of symmetrical configuration, all inductances were equal. But in case of asymmetrical, inductances were unequal. Okay. So what we did to make the inductances equal? We made the lines as transposed. So if lines were transposed, then I can say that ZAA equal to ZBB equal to ZCC, which will be equal to ZS. Similarly, ZAB is equal to ZBC is equal to ZCA, which is equal to Zm. Okay, so we will give them single values in case of a transposed transmission line. Now let us write the KVL equation for these transmission lines. For the phase A, VA minus VA dash will be ZS into IA plus Zm into IB plus Zm into IC. That is, the voltage drop will be due to all the three phase currents. VB minus VB dash will be Zm IA plus Zs IB plus Zm IC. VC minus VC dash will be equal to Zm IA Zm IB plus Zs IC. Now the problem with these equations is that if you see, the voltage in A phase is dependent on current in B phase as well as C phase. So these equations are coupled. These equations are not independent. So if I break it into the sequence components, I will have to see whether or not they become independent. So let me write these equations in matrix form. Delta VA, delta VB, delta VC will be equal to ZS, Zm, 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 Zs, Zm, 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 Zs, IA, IB, IC. Okay. Now we know VABC is equal to A times V012. Similarly, IABC is equal to A times I012. So that means I can write it like this. A times delta V012 is equal to Z matrix into A times I012. That means delta V012 will be A inverse Z A I012. So this whole matrix will be the impedance matrix for the sequenced components. So let us calculate this matrix. So first let us calculate Z multiplied by A. If we multiply it by A was 1, 1, 1, 1 alpha square alpha, 1 alpha, alpha square. Now first row into first column will give me Zs plus 2Zm, Zs plus alpha square Zm plus alpha Zm. Now we know 1 plus alpha square is 0. So alpha plus alpha square is minus 1. So the next term would be Zs minus Zm. Next, if we multiply first row by the third column, we will get Zs plus alpha Zm plus alpha square Zm, that is Zs minus Zm. Then second row into first column, we will again get Zs plus 2Zm. Then Zm plus alpha square Zs plus alpha Zm, that is alpha square Zs minus Zm, because 1 plus alpha will be equal to minus alpha square. Then Zm plus alpha Zs plus alpha square Zm, that will be alpha Zs minus Zm. The next term will again be Zs plus 2Zm. Then Zm plus alpha square Zm plus alpha Zs, that is alpha Zs minus Zm. And last alpha square Zs minus Zm. Now this matrix needs to be multiplied by A inverse. A inverse was 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha. Okay. Now if we multiply this, what we will get is 1 by 3. First row into first column will give me 3 times Zs plus 2Zm. Then first row into second column will be Zs minus Zm multiplied by 1 plus alpha square plus alpha, that is 0. Then first row into third column will be Zs minus Zm multiplied by 1 plus alpha square, again 0. Then next, second row into first column, Zs plus 2Zm multiplied by 1 plus alpha square, that is 0. Then 1 into Zs minus Zm, alpha cube into Zs minus Zm, alpha cube into Zs minus Zm. Alpha cube is 1, so it will be 3 times Zs minus Zm. Then 1 into Zs minus Zm, alpha into alpha will be alpha square Zs minus Zm, alpha square into alpha square will be alpha 4, which is alpha. So it becomes 1 alpha square alpha, it will be 0. Then Zs plus Zm into 1 plus alpha square plus alpha, that is 0. Then 1 into Zs minus Zm, alpha raised to the power 4 into Zs minus Zm, that is alpha Zs minus Zm, alpha square Zs minus Zm, 0. Then 1 into Zs minus Zm, alpha cube into Zs minus Zm, alpha cube into Zs minus Zm, that is 3 times Zs minus Zm. Now this 3 can be taken out common. So this matrix will become delta V0, 1, 2, Zs plus 2Zm, 0, 0, Zs minus Zm, 0. So now if you see, the off diagonal terms which represented mutual impedances are gone and only the diagonal terms remain. That is, we have removed the mutual coupling between the equations. So we can directly write delta VA0 is Zs plus 2Zm into IA0. Delta VA1 is Zs minus Zm IA1. Delta VA2 will be Zs minus Zm IA2. So how will the sequence network look like? In positive sequence, we will have VA1, VA1 dash. Here we will have Z1 is equal to Zs minus Zm. Then negative sequence will have VA2, VA2 dash Z2, which is also equal to Zs minus Zm. Then zero sequence will have VA0, VA0 dash Z0 will be Zs plus 2Zm. So here Z1 is equal to Z2 and Z0 is typically 3 times the Z1. Okay, so that is the relation between sequence impedances of a transmission line. And in case of generator, what we saw, Z1 was greater than Z2 was greater than Z0. In case of transformer, Z1 was equal to Z2 was equal to Z0. In case of transmission line, Z1 is equal to Z0, Z2 and Z0 is 3 times Z1. So that is how, if you are given the same sequence impedances, you can identify the component of the power system. Now let us understand it with the help of a problem. A 25 MVA 11 kV 3-phase synchronous generator has a sub-transient reactance of 20%. So generator reactance is 0.2 pu. The generator supplies two motors over a transmission line with transformer at both ends, having rated MVA of 15 MVA, 7.5 MVA, both 10 kV with 0.25 subtransient reactance. Sorry, this is it is talking about the motors. So this is 15 MVA, 7.5 MVA, 10 kV, 10 kV, and both have 0.25 pu subtransient reactance. Both transformers have 30 MVA. Okay. 10.8 by 121. So this must be 121 by 10.8. Delta star with leakage reactance 10%. So 0.1 pu, 0.1 pu. Series reactance of line is 100 ohm. Now we have to draw all the sequence network assuming equal positive, negative and zero sequence impedances of components. Okay. So the first thing that we need to do is we will divide the power system into sections based on the transformer. Then we have to assume the base. Now let us assume the base same as the generator, that is 25 MVA 11 kV. What will be the base voltage in the transmission line? It will be in section number 2 121 by 10.8 into 11, which is 123.24. And what will be in the section number 3? In section number 3 it will be 123.24 into 10.8 by 121, which will come out to be 11 kV. Now we have got the base for each and every section. Let us determine the value of pu reactances of each and every component. For generator 1, old reactance is 0.2, old voltage is 11, new base is also 11, old MVA, new MVA is 25, old is also 25. So this will be J.2. For transformer T1, the reactance that is given to me in the problem is 10%, rating is 30 MVA 10.8 kV. So we have to assume on one side either the primary or the secondary. I am assuming on the primary. Given voltage was 10.8, assumed is 11. Assumed base is 25 MVA, given was 30. So how much will this come out? J 0.0805. Transformer T2 J.1. Let us take on the primary of this. Given voltage is 121, assumed is 123.24. Given base is 30, assumed is 25. So this will be same 0.0805. For the case of transmission line, reactance given is 100 ohm. We will divide it by base. Base will be V square by S. 123.24 square by S is 25. So this will come out to be J.164 pu. For the case of motor 1, what is the rating given to me? 15 MVA, 10 kV, 25% reactance. So J.25, 10 kV was given, we have assumed 11. Then 15 was given, we have assumed 25. So how much will this come out to be? J.3443. For motor number 2, PU impedance is same. Voltage rating is also same. Just MVA is given to me 7.5. So it will be double of this, that is J.6887. Okay, why double? Because the denominator is halved. Now let us draw this in terms of sequence network. First, let us consider positive sequence. So let me take a reference bus. Then we will take generator EMF, generator reactance. Generator reactance is how much? J.2. Then there will be transformer. For positive sequence, transformer is represented by impedance. Then transmission line. Then again transformer. Then there are two motors connected in parallel. So motor has equivalent circuit same as that of a generator. So how much reactance? J.34 and J.68. This is generator EMF, this is motor 1, this is motor 2. So this is the positive sequence network. Now in the problem they have said assume equal positive, negative and zero sequence reactances. That means negative sequence impedances will remain same as positive sequence. But what is the essential difference between positive and negative sequence network is that there are no induced EMF in the negative sequence network. So for drawing negative sequence, what we will do is we will remove these EMFs. Okay, so we will directly connect like this. This will be my negative sequence network. There will be no EMFs, the rest will remain same. If we were given separately negative sequence impedances, then we will replace positive sequence impedances by negative sequence. Now to draw zero sequence network, we have to consider the transformer connections also. Okay, because zero sequence network depends on transformer connection. Now if you see, first transformer is delta star grounded, other is star grounded delta. So let us draw on this basis. This will be my reference bus. Now neutral of generator is grounded, so that neutral impedance will come as 3 Z generator. Then this will be J.2. Neutral impedance comes as 3 times the neutral impedance. Then transformer is star delta grounded. So series switch will be open. So we will short the shunt switch. Then we will place transformer impedance J0.0805. Then transmission line J.164. Then next transformer is star grounded delta. So on star grounded side we will operate series switch, and on delta side we will operate shunt switch. Series will be open circuited. Then out of the two motors, one has the neutral grounded, one has neutral ungrounded. So ungrounded impedance will come like this, 0.34. When the neutral is grounded, this will be 3Zm and J.68. Okay, because motor 2 has neutral ungrounded. So here Zn is infinity. Okay, so that is why we have shown open circuit. So this way zero sequence circuit, you have to take care about the neutral grounding and the transformer connection. So let us summarize what we covered in this lecture. We first saw transformer sequence network. And there we saw different zero sequence network based on transformer connection. Then we saw transmission line. In transmission line we saw Z1 was equal to Zs minus Zm, Z2 was equal to Zs minus Zm, and Z0 was equal to Zs plus 2Zm. And then we saw how to draw the positive, negative and zero sequence networks independently of each other. In the next lecture, we will look at few problems based on the topics that we have covered so far in fault analysis, and then we will proceed on to how to analyze the faulty conditions in a power system.